Good morning, sir.
Good morning. So today we'll have two sessions, one from now to maybe 40 minutes. I think it will come. Then second session will start at 11:15. So I can record meanwhile. Uh, the recording sessions also I'll share you later. The first one, because in the previous we talked about triangular element, uh, constant strain triangle. The steps will be the similar for axisymmetric elements and quadrilateral elements, right, and the solid elements also. So here in our syllabus we have CST element in three-noded and again three-noded axisymmetric element. So we don't have a four-noded quadrilateral axisymmetric, but the syllabus restricted to three-noded triangular axisymmetric element. So the first session will talk about axisymmetric problem. What is axisymmetry? How and when we'll treat axisymmetric? What is the advantage of axisymmetry? Because instead of solving 3D analysis, we'll simplify to 2D. One such is plane stress, plane strain. The third one is axisymmetry. That's what we'll discuss today. The subsequently after this session, the next session, we'll see the formulation of quadrilateral element and the Jacobian in quadrilateral, stiffness matrix in quadrilateral. Then after that, we'll see the numerical integration, then Gaussian quadrature. So why should we use numerical integration and Gaussian quadrature, and what is the importance of that? Because all numerical approaches, we use Gaussian quadrature. So the solution, what we normally see the nodal, but actually when you use the Gaussian quadrature, our output is at Gaussian points. So how do we consider the Gaussian points? Where exactly the Gaussian points? Is the Gaussian points are going to coincide with nodal points or some other place? So this, once you have a clarifications in future, whenever you do the analysis, you'll be knowing that for every element, the solution is at Gaussian. Later on will approximate to the nodal. So, but actually we print the nodal solution in software, but reality we are calculating at the Gaussian and we truncate or approximate the solution to nodal. So how do we choose those and all? We'll discuss the second session. So I just share my PPT for you all, then we'll go ahead. So will you see the screen now? Are you able to see the screen?
Yes, sir.
Yes, sir.
Okay. So the axisymmetric, if you see the cases like you have a full cylinder, then we are cutting about vertical axis, and this is going to be the model, and 2D, and it coordinates changes to instead of x, y, z, or theta, z. So the radial direction r and z direction, you have a y is a z direction. So theta is a circumferential. So this is a plane that we are considering for axisymmetric analysis. Similarly, here the solid is shown on the right extreme. The same when you see a plane section out of it, the plane only analyzed. After getting analysis, we can revolve it, you can see 3D form. But reality analysis is done in 2D. So this is the way we'll do in axisymmetric cases. We have a lot of applications of axisymmetry. You have flywheels, you have gears, you have cylinders, where thin or thick, and then plates and cooling towers, nozzles. So the many of the applications you would see, we'll treat instead of 3D analysis, we'll go for 2D because the solution is going to be same, and which simplifies your time for calculation. That's the scenario. If you see here, one of the model where you have a symmetric about vertical axis, we can cut off section and we can analyze this. And here ring-like member, we can take only plane section. The plane is shown here. So analysis, instead of total 3D solid, we can do only 2D plane alone. And that plane alone is shown here in two-dimensional. Similarly, we can have a cylindrical ring here, internal pressure or external pressure, any symmetrical load. See, again here, there are two cases. One is the symmetrical axisymmetric geometry and axisymmetric loading. The second is axisymmetric geometry and antisymmetric loading. The antisymmetric loading, we don't have any syllabus, but antisymmetric loading also we can treat, but that is not part of it. So whatever we are considering here in this session is only axisymmetric geometry and also axisymmetric loading. So here ring the uniform pressure or constant load, which is going to be a ring type load, then you can consider as one ring and analyze. Even instead of a ring, you can, what you can do, if you take a ring, it's a plane strain. You can take in the quarter, then you can do the axisymmetric analysis. And one such element you can plot here and do it so. Similarly, a cylinder subjected to UDL load on the top, we can cut it and you can take only half of the cylinder and you can model as axisymmetric member. So here a flywheel which is subjected to UDL load like, so then you can take only quarter symmetry, this quarter symmetry, and you can analyze. This is the electrical member where all the the thermal aspects and when voltage is increased, there is a change in current. By that, the temperature change will be there. So quarter symmetry of the model is shown here. Here also, the axisymmetric of small section is shown here. When you revolve it, it is going to be 3D solid. So rather, 3D we do 2D analysis. These are typical cases where we have different analysis. You can see the member and symmetry of the same object. You can see the member and you can cut section, you can see. And this is analysis of 2D member. This is full revolution of the plane is analyzed and shown as a 3D, but actual analysis is only 2D. This is also same, analysis is 2D. We have one section and which can be revolved about the vertical axis. It forms complete 3D solid because everywhere ring, the solution is going to be same. That's what is the meaning of axisymmetry. Here, then you can have a member subjected to internal pressure. There are different components. Even we can analyze some of the components which we can remove, and axisymmetric part we can do separately. This will be transferred to assembly of the solutions. What is axisymmetric solid? So when a plane section revolves about certain axis, then it forms a complete 3D solid. Rather analyzing 3D solid, the analysis is performed only on plane section. So that is called axisymmetric member, axisymmetric loading, axisymmetric geometry. So whatever analysis you perform, you can say axisymmetric analysis. You could see this here a ring type structure. So you can have a very diameter, also R tapered, you can have a different kind of things. So here, one plane section is a triangle. If you take and your axis of revolution is Z axis. So you can revolve about X axis or revolve about Z axis or any other axis. So here revolving axis Z. This plane triangle, if you can revolve about the Z axis, it forms a complete 3D solid. For such a case, you can do 3D analysis as it is by discretizing into 3D elements. And to simplify the solution time, we can go for plane section of only plane triangle. And this plane triangle can be modeled and subjected to loading and boundary conditions, and solution can be obtained. That is called axisymmetric analysis. Typically, what we do, x-axis generally represented by radial axis, or the normal axis y is represented by z-axis. Then we have a theta. This theta is anywhere in the ring at a particular radius. What is going to be your output? So any angle you can find at a particular radius output. These are all called circumferential strains or stresses or circumferential variation. So that is theta. So you have cylindrical coordinates r, theta, z. Every axisymmetric member, though it's a plane, plane is rz, and theta is revolved anywhere, any angle. Theta is 0 to 2 pi. Any angle, anywhere output is going to be same. That theta, 20 degrees, 30 degrees, 50 degrees, you can have output. So instead of Cartesian coordinates, the axisymmetric members will be in terms of cylindrical coordinates. So the z-axis is called axis of symmetry or axis of revolution. Each vertical cross section of the element is plane triangle in this case, or plane, any plane of rectangle like. So what we learned from here, know about axisymmetric solids, then have the relation between stress and strain, then formulate axisymmetric problems. Means you can formulate for the traction forces, then body forces, then concentrated forces, then stiffness matrix, stiffness and displacement equal to force. Then you can solve for the deflection, then strain, then stress. The approach is same. The outcome, understand about axisymmetric solids, differentiate the relationship between stress and strain, solve the problem related to axisymmetry. Because in axisymmetry, we are changing Cartesian to cylindrical coordinates, your stresses and strains, right, measured in terms of r, theta, z. Typically, you can see the member you can have on the top side. We have shown the circumferential coordinate system at an angle theta from the axis to any radius you can see. And you have a cut section of the plane. This plane can be revolved about the vertical axis. Then it forms complete solid. This is the axisymmetric solid. And you can have the examples like cooling towers, water reservoir, water treatment plant, cylindrical tank. So whether it is going to be cylindrical or spherical, right? So different shapes you will have. And sometimes we take axis of symmetry, maybe radial axis, or axis symmetry, maybe z axis. So depending on the member, how the member is oriented, and accordingly we will try to find out. Whenever we have written in the first class that the equilibrium equations for Cartesian coordinates in terms of sigma x, sigma y, sigma z, dou x, dou y, dou z, and tau x, y, tau y, z, tau z x. So you have 6 components of stresses: sigma x, sigma y, sigma z, tau x, y, tau y, z, tau z x. Accordingly, epsilon x, epsilon y, epsilon z, gamma x, y, gamma y, z, gamma z x. Same way for cylindrical coordinate system, for the same we can write sigma x by sigma r, dou x replaced by dou r. And same way you can have sigma theta, sigma where you have sigma y. Then you have sigma z. The sigma z is similar to the sigma z there also. And in addition to that, you have tau r theta, tau theta z, then tau r z. These are shear stresses. Then xr, y theta, zb are the body forces induced on the member. So this is stress equilibrium. Same way strain equilibrium, can write sigma replaced by epsilon. So strain equilibrium. Sometimes in the exam when they ask, write the equilibrium equations for 3-dimensional, ask the equation for cylindrical coordinates for any 3D solid member. This will simplify to our plane axisymmetric member. Similarly, if you write the strain displacement relationships, radial strain dou u by dou r, circumferential strain epsilon theta 1 by r, dou v by dou theta plus u by r, epsilon z, strain in z direction, tangential strain, dou w by dou z. Gamma r theta 1 by r, dou u by dou theta plus dou u by dou r minus v by r, gamma r z, gamma r theta z, similarly written. Because it is going to be small, sometimes these members will be very zero in case of the 2-dimensional plane cylindrical coordinate member. If you write stress strain relationship, this is a D matrix for 6 components of stresses, 6 component strains. Whether it is a Cartesian, whether it is a cylindrical, this D matrix won't change because it depends on Young's modulus Poisson's ratio. And you have a 6 components of stresses, 6 components of strain. The 3-dimensional member, whenever you write in a Cartesian or cylindrical, your D matrix is going to be same, because stress equal to strain, your proportionality is the D matrix, material matrix. So for axisymmetric members, when you consider gamma r theta z 0 in the above equation, tau r theta z is 0, Then epsilon r becomes dou u by dou r. Epsilon theta simply u by r. Any radius, that angle, you can measure the radial displacement by the radius is simply circumferential strain. Then tangential strain is dou w by dou z, and shear strain in the plane RZ dou u by dou z, dou u by dou z plus dou w by dou r. These are the four strains. Correspondingly, you can have sigma r, sigma theta, sigma radial stress, sigma theta tangential, circumferential stress. Then you have sigma z tangential stress, then shear stress tau r z. And when you see schematically the variation, as I said, any element, if you take small element du, when you take it an angle theta, the angular difference is d theta. In this d theta, what is going to be radial displacement? So u becomes, in the small strip, u place dou u by dou r dr. This dou u by dou r is the radial strain that you can see. And in the case of circumferential, any angle theta, you have epsilon theta is at a radius. What is the radial displacement? That is going to be u by r is your epsilon theta. When you go for epsilon z, you can have epsilon z is dou w by dou z. So you can see an element of this rectangular wise, when you have the small differential change in the member, then you have a change here, change there, angularly, the orientation changes. And this you can find dou w by dou r dr, and the radial side u plus dou u by dou r dr, and z side means y here in a normal case, but here in r theta z is normal. So the differential variation, the w is dou w by dou z into dz. So dou w by dou z is your epsilon z, and your shear strain is, you can have both together. So dou u by dou z plus dou u by dou r is dou w by dou r is going to be your the shear strain. So the same you can write for stress components, or you can substitute zeros in the original one. Whatever other things are not there, then corresponding strain stresses you will get. Once you separate strains, you get D matrix. This is the 4x4 elastic matrix for axisymmetric solids. Because axisymmetric solids, you have four stresses corresponding to four strains. Your D matrix. When you write stress strain, you can find this 4x4 matrix. So it is in terms of Poisson's ratio and Young's modulus. The stresses, if you see the small strain, elemental volume of the angular member, whenever you rotate about the z-axis here, the stress components are shown. You have all the three stress components. You have a radial stress sigma r, tangential stress sigma z, circumferential sigma theta. The sigma theta is at any radius circumferentially oriented. Then in addition to that, you have a shear stresses that tau r z or tau z r, because in this is going to be isotropic, they're going to be same. Typically, when you take an axisymmetric member, you can take small strips. So small strips subjected to traction loads, subjected to body forces, subjected to concentrated forces Pi, and the area is A, then maybe the UDL concentrated tractions are shown in this. And this member you can discretize into small triangles, and each triangle is separately analyzed. So when you see the displacement function, here x direction is r direction is u, z direction y is z here, z direction is w. So your displacement function in any point in the given section, you can see that there are two translations, one in radial, other is tangential. Radial is u, tangential is w. The traction you have radial PR, tangential PZ. Body force is radial FR, tangential FZ. Constant force radial PR and tangential PZ. So stress strain, you can have that member, yeah. So then you can calculate total energy in the member using potential energy approach. So potential energy is nothing but strain energy minus work potential. So strain energy, your volume integral becomes half of 0 to 2 pi. Then area means dr d theta is gone here, dr dz into r. So here you have sigma transpose epsilon r dA d theta. So sigma transpose epsilon is your energy, right? So r dA d theta is your volume. Then similarly, due to body force, the body force, whatever you have F, and this is a volume. So force per into volume into volume is a force into displacement is the work done by the body force. Similarly here, work done by traction force. Traction per unit area into this is area r dl d theta. Dl is the segment length, the differential length into angular position into r is your area. So traction per area into area is your traction force into displacement is work. And whenever you have a constant force, that into displacement is a work. So energy minus all the force that does work is a total energy system. This total energy we can differentiate with respect to the displacements concerned and equal to zero. You get the simplification stiffness matrix into displacement equal to force. So those vectors are shown here. Then when you write a strain matrix, as you know, epsilon is epsilon r, epsilon z, gamma r, z, epsilon theta, dou u by dou r, dou w by dou z, dou u by dou z, plus dou w by dou r, and u by r. Here, how the arrangement do you see? If you have considered epsilon r, epsilon z, gamma r, z, epsilon theta. If you want to write epsilon r, epsilon z, epsilon theta, gamma r, z, or some people write epsilon r, epsilon theta, epsilon z, gamma r, z. So accordingly, your D matrix corresponding terms will be changed. Then similarly, stress matrix, radial, tangential, shear, and circumferential. As you know, sigma equal to d epsilon, and here corresponding variation in the element wise, radially, tangentially, shown with the deformation change. This is a discretization process that we have done to some 21 elements. Each one is a triangle element. Each element you can find out the stiffness. Then afterwards, all 21 elements stiffness you can assemble so. It is similar to the procedure adapted is similar to whatever we have done for constant strain triangle. So typically, if you take a triangle element, circumferentially, when you show the whole volume look like this, and at node 1 you have two displays, one in radial direction Q1, the other one is tangential Q2. Similarly, here Q3, Q4, Q5, Q6. Anywhere in the plane, your displacement function is x direction, radial direction U, tangential direction Z. Then you have the coordinate, global coordinate, anywhere is RZ. And here your displacement measurement could be Q at R or QR, QZ, we can say. So the displacements you have 3 in radial direction, 3 in tangential direction. Then each node you can have a 2 degrees of freedom of translations only. Therefore, this element also have 3 shape functions n1, n2, n3. So you have u bar equal to nq. So your n matrix n1 0, n2 0, n3 0, u direction, and 0 n1 0, n2 0, n3 in w direction. So w is nothing but y in CST. So you have 2 by 6 matrix. Similarly, components of q's you have column matrix 6 because q1, q2, q3, q2, q6. So u bar is nq when you multiply n1 q1 plus n2 q3 plus n3 q5. Similarly, v equal to you have n1 q2, n2 q4, n3 q6. Now, if you replace n1 by xi, if you want simplify to only 2 variables, then n2 is eta, n3 you know 1 minus n minus eta because n3 is 1 minus n1 minus n2. So if you substitute those in the above equation, replacing by n1 by xi, n2 by eta, n3 by 1 minus n minus eta per u. Similarly, w, you can have n, this is u is summation ni q I 2i minus 1. Here w equal to summation I equal to 1 to 3. You have n of 2i and q of 2i. So you can have I equal to 1 to 3. Then accordingly you will have w is xi q2, eta q4, 1 minus eta q6. Then you can take out the xi. You can write q1 minus q5 plus eta times q3 minus q5 plus q5. Similar w you can write when you take out xi q2 minus q6. When you take out eta q4 minus q6, then q6. Same way you can write the isoparametric presentation of the element replaced by u by r, then accordingly q by geometry. So r equal to summation ni ri. So NIRI becomes, when you expand N1, N2, N3, that becomes N1 is xi, xi R1, N2 is eta, eta. Then you have here not necessary 3 here R2 only. 1 minus eta here also you can have R3. Not necessary to have, because when you say 1, 2, 3, here only 3. That correction you can change it. R1, R2, R3. So similarly, Z equal to xi Z1 eta Z2 1 minus z minus eta Z3. Now you can differentiate, because we have to go for partial differentiation. So we adapt chain rule of partial differentiation, because u is a function of R and uh, Z, and w is a function of R and Z. R is a function of same xi and eta. Z is a function of xi and eta. So u w is a function of xi eta. R z is a function of xi eta. Therefore, you have to go for chain rule of partial differentiation. When you adapt dou u by dou xi, you would get dou u by dou r into dou r by dou xi plus dou u by dou eta by dou r. So that when you simplify dou u by dou xi, dou u by dou eta, Jacobian into dou u by dou r, dou u by dou eta. So the same, I can show you the next slide, that dou u by dou xi, what you get is dou r by dou xi of dou u by dou r, dou z by dou xi of dou u by dou eta. Dou u by dou eta is dou r by dou xi into dou u by dou r, dou z by dou eta into dou u by dou xi. So this matrix we call Jacobian, and dou r by dou xi, dou z by dou xi, dou r by dou z by dou eta you can get from this matrix, that equation. So that if you see, when you find dou r by dou xi, you get R13, because here only mistakes are there, R1, R2, R3, right? So that you can correct it. So you have R13, Z13, R23, Z23 is the terms of this, because these are all constants. And you have a function of dou u by dou r, dou u by dou z. Because directly we cannot get dou u by dou r, that's why chain rule of partial differentiation we are going for getting dou u by dou xi and dou u by dou eta in terms of dou u by dou r, dou u by dou zeta. Now dou u by dou r you can find out from this equation. Dou u by dou r is, you can find from here, right? Because this is written in terms of xi and q's. And dou w by dou xi, dou w by dou eta, from this you can get it. So when Jacobian is that, then Sheff functions, whatever we written ni, are n1, n2, n3, or if you say 1, 2, 3 replaced by ijk, ni, nj, nk. Sometimes we represent by capital Li. Capital Li is in terms of area coordinates. So instead of ni, we sometimes in the books they write Li. So Li, ni is going to be same. nj, lj, nk, lk is 1 by 2i. Suppose if we represent the coordinates for every node, then we can have constant A at ith node plus constant B at ith node into R plus constant C at ith node into Z. So we are writing this triangle element in terms of linear form, because you have 3 degrees of freedom at each, 6 degrees of freedom in the element, but 3 degrees of freedom in radial direction, 3 degrees of freedom in tangential direction. So radial, 3 variables are there, you can have 3 constants, and tangential you have 3 variables, 3 constants. That's why we have represented by AI, BI, CI. So linear written A, BI and CZ, AJ, BJ, R, CZ. So you can have this, and you can go for area of the triangle by finding your coefficients, then half of that, whatever you get it, when you substitute AI and all, you can get those. So determinant of J is that, now whatever you have here, dou u by dou r, dou u by dou z, if you take out on the left side, inverse of this, inverse you can get here, into dou u by dou z, dou by dou eta. Dou u by dou z and all, you can get it from here. So therefore, you can find out that dou u by dou r, dou u by dou z, Jacobian inverse into dou u by dou xi, dou u by dou eta. And you have an equation, you can get these two, and you have a W equation, you can get these two. Then you have a radial strains, you have a tangent strains, and shear strains, you can get solved. So that's what we have shown here, dou u by dou xi, dou by eta. When Jacobian inverse, you do so. Then strain is in the element, radial strain, epsilon r, dou u by dou r. Then you have dou w or v. Sometimes we write v also. Dou w by dou xi tangential. Then shear, dou u by dou xi and dou v by dou r. So you have a tangential. V replaced by w also you can. Then the circumferential chain u by r. So then u dou u by dou r you can get from here. Dou u by dou r is the Jacobian, whatever you have first row into the column of this. Similarly, if you want this dou w by dou xi, dou w by dou r is first row into this column, right? Once you do so, you can substitute here radial strain in terms of z and q's, in terms of z, terms and q's and j, and r's and j. Here both the r and z will have j. And here you have epsilon theta is u by r, u is n1 q1 plus n2 q3 plus n2 q5. Only radial direction displacements. Shape function at node 1, displacement radial direction at node 1. Shape function at node 2, radial direction displacement at node 2. Similar shape function at node 3, radial direction displacement at node 3. So this you will get epsilon. Then here you can separate your coefficients of z and r, and q separate, q1, q2, qc. So the B matrix you get it, that you can see here. So the epsilon matrix, then here, this is a B matrix, what you can see. So epsilon is BQ, Q is Q1, Q2, Q3, Q4, Q6. So you have a Q1 to Q6. This is your B matrix. So then the stiffness matrix is, because here again, you know that the B matrix, all elements are constants. Then because this R is a variable. Suppose if you calculate R at centroid, R bar, when you write R bar, then this B matrix becomes B bar. B bar is nothing but finding the B matrix at the centroid. Centroid radial coordinates R bar is R1 plus R2 plus R3 by 3. Then your stiffness matrix is area integral becomes A. Then circumferential 0 to 2 pi is 2 pi. So 2 pi R bar area B transpose dB. This B bar is nothing but B matrix evaluated the centroid. So all these are constants, so that stiffness matrix you can find out R bar is given R1 plus R2 plus R3 by 3. Otherwise anywhere R, so R value should be given so that you can find B matrix. Accordingly, you can substitute in your stiffness matrix and get it. So area, 2 times area is determinant of Jacobian. If you want area, half of determinant of Jacobian. Suppose if you go for traction forces or body forces, accordingly equivalent force you have to calculate, then you can multiply with the displacement. So that equivalent forces calculated, this bar means calculate the centroid. Similarly, if you take a simple cylinder subject to internal pressure, and we can cut the section, and you can have one rectangular area. So this area is divided into 2 elements. So we have first element nodes 1 to 4, second element nodes 2, 3, 4. So any order you can give, the dimensions are given to you. And we can have element 1, 2. Element 1 connection is 1, 2, 3, 1 to 4. Element 2 connection is 2, 3, 4. Same way, then nodes are 1, 2, 3, 4 nodes, nodal coordinates are given. First, you can know the Young's modulus value is given. So then Poisson's ratio. You can substitute in your D matrix where Young's modulus and Poisson's ratio. You would find D matrix. Then you can get Jacobian. So J is, you know, R13, Z13, and R23, Z23. So you can substitute there. You can find Jacobian because coordinates are known to you. So once you know the coordinates, you can get the area of the triangle, that is half of J. Now, you know all the coordinates of this element, then you see the forces acting. So this pressure is acting here. The pressure converted to be forces, F1 and F3. The pressure value is 2 megapascal. So you have a circumferential length 2 pi into this length is 10 mm. And this radius 40. So 2 pi r 40 into 10, the pressure by 2 is the force at this point and that point. So we calculated the force F1 and F3 equal to 2 pi r, the length of the element, into the pressure acting by 2 gives the force at both the nodes. It is acting radially outward. So inside it is acting. So centroid, if you want to calculate, R bar is 1/3, R1 plus R2 plus R3. So you get those. Then B matrix is the centroid, that whatever we are given equation, substitute there, and R bar value is known. Similarly, second element you can calculate, then multiply D into B1, then D into B2, then these 2 matrices you have to add according to degrees of freedom. Then you can get K1 matrix, K2 matrix. These two matrices you can add, you can get global matrix. Then substitute the boundary conditions. You can see the boundary conditions here. So here you have a radial, then tangential. So here you can see the y direction it is constrained. Here y direction is constrained, means z direction. Means here Q1, Q2 here, Q3, Q4. So Q3 exists, Q4 is 0. And Q1, Q2, Q2 is 0 here. And only two displacements are there here. One is Q1 exists here, Q3 exists. And here Q5, Q6, 0, Q7, Q8, 0. Those, if you substitute in the given matrix, only finally you get 2 by 2 matrix. You can solve for that. So you have a displacement at node 1, displacement node 3, remaining are zeros. This is the output for you. Similarly, you have a triangle axisymmetric member is given. Then all the coordinates are given to you. Then find the shape functions corresponding node degrees of freedom at the element. So coordinates are given, RZ values are given. Then you have to calculate the shape functions. So Ri, Zi, Rj, Zj, the coordinates are written. The shape functions you can write in terms of Rz. Those shape functions, when you write and area, then the coefficients Ai, Aj, Ak, Bi, Bk, Ci, Cj, Ck coefficients are there. Substitute in area, then you would get those values. Then accordingly, Ni, Nj, Nk you can write. Then substitute here that A, B, C values, you would get the shape functions. Then your B matrix you can have in terms of those coefficients. Then B matrix at the centroid you can calculate as B bar, the centroid R1 plus R2 plus R3, those values you can delete. So this is simply substitutes if you can understand the actual the formulation. So and similarly, the same element considered for problem 2 are given Young's modulus 207 gigapascal and Poisson's 0.3. So those two given stiffness matrix, you have to calculate, as you know, 2 by R bar area we calculated earlier. B bar, D, B bar is there. So your D matrix, you can substitute E and Poisson's ratio. And D, B, K, and 2 pi R if you multiply. 2 pi R is there. D and B earlier calculated. These three matrices you have to multiply. You get the stiffness matrix of global. So the total matrix you would get it. If you go for a body forces, typically a body force could be a centrifugal force. So I've shown this member is revolving about vertical axis with angular velocity omega. So volume integral shape function transpose body force over a volume. So here rotation you can take out 2 pi 0 to 2 pi into d theta is 2 pi. Then area integral shape function transpose. You have a radial direction RB, then tangential direction ZB. So the radial direction is centrifugal force omega square R. So R is located at this point. Then you can substitute these two, integrate, you will get the body force in radial direction and tangential direction. So at a particular value of the magnitude, you can have shape function Ni 0, 0, Ni, then RB, Rz. Then you can multiply them, integrate the area integral. Then you can get the value of the magnitude for the forces, the radial direction, tangential direction at each node. Even every node you can calculate. At each node is given 3 nodes. 3 nodes we can have 6 components. Same attraction force, you can have any edge you can take. So J and M edge, there is a constant pressure is acting. So you can calculate those as the forces here and forces there. So we have to calculate the forces in radial direction tangential here, radial direction tangential there. So shape function